This video summarizes a 2024 study published in Physical Review E that investigates the behavior of polarizable polymer chains subjected to external. The fundamental question addressed in this study is how induced dipoles and polymer chains interact among themselves under an externally applied far-field electric field, and how these interactions influence the chain's conformation and mechanical properties. This question is important because prior models have largely neglected the long-range dipole-dipole interactions and considered only direct applied field-dipole coupling, potentially leading to significant inaccuracies in predicting polymer behavior. The authors approached this problem using a self-consistent statistical field theory, incorporating a worm-like chain model with coarse-grained polarizable segments. This framework captures both entropic polymer conformations and the detailed electrostatic interactions, including the nonlocal, long-range dipole-dipole forces that decay with the cube of distance. By doing so, the study aims to provide a more accurate and physically grounded description of how the polymer chain responds mechanically and structurally to applied electric fields, highlighting the importance of correctly accounting for all dipolar interactions in such systems. Figure 1 illustrates a polarizable polymer chain placed in an externally applied far-field electric field, denoted as E0. Each segment of the polymer chain becomes polarized, inducing dipoles aligned in response to the electric field. The key physical insight here is that these induced dipoles do not act independently. Rather, they engage in dipole-dipole interactions that are long-range, decaying proportionally to the inverse cube of the distance between segments. These non-local interactions influence the overall configuration of the polymer chain and, importantly, affect its mechanical response. The authors emphasize that prior studies that neglected the dipole-dipole interactions, considering only the coupling between the applied field and individual dipoles, introduce large errors in modeling results. This demonstrates the necessity of incorporating the full dipole interaction network for accurate predictions of chain behavior in an electric field. Figure 2 introduces the kinematic quantities that are used to mathematically describe the polymer chain configuration. The authors model the chain using a worm-like chain WLC approach known for capturing the semi-flexible nature of polymers via a persistence length parameter denoted lambda. The chain consists of n coarse-grained polarizable segments, each of length A, with a total contour length LC equal to a times n. The ratio of persistence length to contour length, lambda over LC, determines the polymer's flexibility. They consider a highly flexible polymer using a small ratio of 10 to the negative 3. The chain configuration is represented as a continuous three-dimensional space curve RS, where S is the normalized chain contour coordinate ranging between 0 and 1. The figure also depicts partial chain partition functions used in their statistical mechanics framework to describe the likelihood of subchain conformations based on position and orientation variables. This detailed kinematic and configurational description enables incorporation of both entropic elasticity and electrostatic interactions in a self-consistent manner. Figure 3 presents the baseline scenario where dipole-dipole interactions are neglected, allowing this to compare with subsequent results, including them. Here, the authors fix the polymer chain ends to impose an end-to-end vector length of approximately 1.5 times the square root of n. They apply a uniform far-field electric field, indicated as E hat0, with magnitude roughly 1 along the E2 direction. The panels in Figure 3 show the resulting electric field distribution, chain segment density, and polarization under these conditions. The electric field is spatially constant and equal to the applied field, as expected without dipole-dipole effects. The chain segment density is concentrated mostly near the fixed ends, reflecting the constrained geometry. The polarization, representing induced dipoles, is negligible on the chosen scale, indicating almost no collective dipole effect without dipole-dipole interactions. This figure serves as a crucial reference to highlight the impact of including dipole-dipole couplings in later figures. Figure 4 provides a direct comparison of the polarization distribution in the polymer chain, without and with dipole-dipole interactions. for two distinct orientations of the applied electric field relative to the chain: parallel at theta equals 0 and perpendicular at theta equals pi/2. In both orientations, the left panels depict the polarization distribution neglecting dipole-dipole interactions, while the right panels include these interactions. The arrows in the figures show the vector direction of the polarization, and the background color quantifies its magnitude. Strikingly, the polarization magnitude when accounting for dipole-dipole interactions is at least an order of magnitude larger compared to the case when they are ignored. This underscores the substantial role these long-range interactions play in enhancing the collective dipole response within the polymer chain. Thus, the authors interpret this difference as highlighting the critical need to include dipole-dipole interactions for an accurate portrayal of the electrostatic behavior inside such chains. In Figure 5, the authors explore how the orientation of the applied electric field affects the polymer chain's electrostatic properties, with full accounting for dipole-dipole interactions. The magnitude of the applied field is fixed at 1, while its angle, theta, is examined for the aligned case, theta equals 0, and the perpendicular case, theta equals pi/2. The figure shows the electric potential, electric field, and polarization distributions for these orientations. When the field is perpendicular to the chain's end-to-end vector, the dipole distribution is approximately uniform along the chain. Conversely, when the field is aligned with the chain, the dipoles tend to concentrate near the chain ends. Similarly, the electric field distribution is more uniform under perpendicular alignment, whereas it concentrates near chain ends when aligned. Furthermore, the local strength of electric potential, field, and polarization is higher when the field is perpendicular rather than parallel to the polymer chain. The authors interpret these findings to highlight that the electrostatic response of the polymer is highly sensitive to the relative orientation of the applied field and polymer conformation when including dipole-dipole interactions. Figure 6 examines the elastic response of the polymer chain when the applied electric field is perpendicular to the chain's end-to-end vector, specifically with theta equal to 0. The authors plot the force exerted by the chain when stretched against the stretch length. The insets provide spatial maps of the electric field and polarization distributions at 3 stretch lengths, 1, 2, and 3 times the square root of an, respectively. The arrows on these maps show vector directions, and the color reflects magnitude. As the chain is elongated, the polarization and electric field remain relatively uniformly distributed along the chain, but they become increasingly concentrated along the chain's end-to-end vector. Despite these changing distributions, the authors note the elastic force response is essentially unchanged, implying that the mechanical stretching behavior is decoupled from the electrostatic rearrangements under this field orientation. The authors interpret these observations as evidence of significant electrostatic reorganization without a corresponding influence on the chain's basic mechanical stiffness in this configuration. Figure 7 explores the elastic response of the polymer chain for the case when the applied electric field is aligned with the chain's end-to-end vector, corresponding to theta equals pi/2. Similar to Figure 6, the plot shows the force versus stretch, with insets of electric field and polarization distributions at increasing stretch lengths. Here, the authors observe that both the electric field and polarization are concentrated near the polymer chain ends throughout the stretching process. While the magnitude and spatial concentration of these fields change with chain elongation, the overall elastic force response remains largely unaffected by the orientation of the applied field. This suggests that although the electrostatic distributions inside the polymer chain vary substantially with electric field direction and chain stretch, the mechanical elasticity of the chain is robust and insensitive to these electrostatic rearrangements. The authors interpret this as evidence that the dipole interactions strongly govern electrostatic spatial patterns, but do not significantly alter the chain's mechanical force extension behavior in their studied regime. To conclude, This study highlights the vital importance of including long-range dipole-dipole interactions within polarizable polymer chains subjected to external electric fields. Neglecting these interactions, as common in prior models, leads to severe underestimation of polarization magnitudes and misrepresentation of spatial dipole distributions. Using a worm-like chain statistical field theory model, the authors show that dipole-dipole interactions drastically amplify the polarization response and strongly influence how electric potential, electric field, and polarization distribute along the chain. The polymer's response is highly sensitive to the orientation of the applied electric field relative to the chain, modulating the localization of dipoles either uniformly along the chain or concentrated near the ends. Nonetheless, the mechanical stretching behavior, measured by force against extension, remains remarkably stable across different field orientations and dipolar configurations, indicating a decoupling between electrostatic reorganization and elastic mechanics in this system. These insights have implications for designing and interpreting electroresponsive, soft polymer materials and stress the necessity for comprehensive modeling of dipolar interactions in such systems.